Okay, so in the last lecture we were discussing the kinematics of deformable bodies, and we had defined the deformation map, and then we had defined our deformation gradient, which was the second order tensor defined as this. Okay, and in the index notation we had written the components of this second order tensor as something like this. Okay, so using this deformation gradient tensor, we had defined the Jacobian, which is basically the determinant of this tensor, and we had shown that for a volume dV naught in the reference configuration, the mapped volume, which is let us say dV, then the relation was basically this. Okay, using the deformation gradient, we had said that a material, let's say an infinitesimal vector in the reference configuration, deforms or goes to in the deformed configuration through the following rule. Okay, any questions in this? Any problems, any questions, any doubts in this? So this is what we had covered in the last lecture, and today, so after this we had looked at what are the time derivatives, what does it mean by d by dt of a spatial field. Okay, let us say you have a spatial field, and if you're writing capital D by dt of that spatial field, that basically means that you are taking the partial derivative in time of the material field, corresponding material field, keeping the material particle constant. Okay, this is what the material derivative that you guys know actually means. Okay, so you are supposed to keep the capital X constant, that is, you are tracking the same material particle, same guy coming from here, you're tracking it at different times and it's at different spatial locations. Okay, so we had said that this d, capital D by dt of, let us say, a property is basically okay, because this t is a function of the spatial coordinate and time. So when we are differentiating it in time, keeping the capital X constant, we have to differentiate second argument, first argument, we have to take both. Okay, because both first and second argument can change. The only thing that doesn't change is capital X. Okay, so it's not like your usual partial derivative where there's a function of, there's a function that takes two arguments and you're differentiating with respect to one or the other. Here your arguments themselves are function of a parameter and you're differentiating with respect to that parameter, and that parameter here is time. Okay, so basically this material derivative is just a chain rule, and this we had written is basically u dot grad of t. So in the similar sense, you can define acceleration of a particle. Let us say you're defining acceleration, let's label it with this capital A, and that is for a particle. Okay, and the definition of acceleration is again d, or rather del v by del t, again this being a function of capital X comma t, keeping capital X constant. Okay, so this is something that you guys should be familiar with. It's a particle that is moving, you're just differentiating its velocity in time to get the acceleration. The only complicated notation here that it is trying to reinforce is that you are differentiating the positions of the same particle, because now you have a collection of particles which may be moving with different velocities. So you're trying to enforce the fact that you're differentiating position of the same particle. So the same acceleration you can define in the spatial coordinates following this as d So this is del by del T of Lagrangian field or material field. Then you convert it into, when you convert to spatial field, you have to use a material derivative and this. So the acceleration is basically okay. This is what we call as acceleration. Now there are two ways to interpret this term. Okay, this term should be straightforward. There are two ways to interpret this term. One way is to look at it as, so this is u dot nabla of u. Okay, so in a way you're taking the partial the directional derivative of velocity, along the velocity itself. Okay, so if let's say these are the lines which are called the streamlines, let us say, and you have velocity basically a tangent on these lines. Okay, then what you're doing is you're at an infinitesimal, over an infinitesimal length. What you're saying is as the particle moves from here to here, okay, how does the velocity change? Okay, now notice that the particle may not necessarily follow the path over a streamline. Okay, because the particles follow a line which is called what? A given particle's trajectory, what is it called? तीन लाइन थी, कुछ भी बोल दो, क्या ही फर्क पड़ता है. It was the path line. Okay, the trajectory of a particle is a path line. Okay, trajectory of a particle is a path line. So streamline doesn't necessarily tell you what is the trajectory of a particle. Only when the field are steady, then these are same, otherwise they are not. So it may happen that locally the particle is here, the streamline is like this, and your path line may be something else. Okay, so you are trying to look at, there is a particle, it has a velocity, so as it moves in this velocity, with this velocity, what is the rate of change of that velocity? And that is what this term gives you. And particularly this term tells you, okay, when the particle comes here, its velocity would have changed. Its velocity would have changed because you're defining a velocity field. You are saying that velocity of all particles here is, let us say, u1 vector, and the velocity of all particles here is u2 vector. So when the particle moves from this position to this position, its velocity has changed. The change is due to the variation of the field u. So again, this is a field. The velocity is now a field, and it is not something which is attached to a particle. It is attached to a spatial coordinate now when we define fields. Okay, fields don't care if there is a which kind of particle there is. Fields are just saying that you have a velocity at this particular spatial location. So when particle moves to that location, it has a different velocity now. Okay, so that is what this term is telling you. The other way of interpreting this term is you're taking a dot product with something very fundamental in fluid mechanics, and that is called the velocity gradient. Okay, so you can simplify this term. The gradient of velocity by definition is going to be del uj over del xi e hat I tensor e hat j, or just if you want to just write it like next to each other, that is also fine. Okay, so this is the definition of your gradient of velocity. And in the index notation, if we try to simplify this term, what do we get? So we are going to write uk e hat k dot del uj over del xi e hat I e hat j. Okay, what does this become? So again, these are scalars, their order of difference multiplication doesn't matter. So you get e hat k dot e hat I e hat j. What does this give you? Delta what? Delta ik. So this is equal to uk del uj over del xi delta ik e hat j, which is, so you swap out k and I, k with I or I with k, whichever one you want. So you get this. So, this term from the simplification also you can see it is a vector, okay, it is a vector, and usually this is called the convection of velocity. So, any term that we get in material derivative, this term is basically telling you the changes due to convection. Now, convection here does not mean the regular convection that you might have studied in heat transfer courses. Convection basically means the fluid is being transported. As a result of that transport, what is the change in that property? Okay. In the specific case of velocity, this term you will see in some textbooks or articles, you will see it written as advection instead of convection. Okay. So, it is called advection in some in some literature. Okay. So, they are basically telling you about the same term, which is the spatial derivative term in the material derivative. Okay. Now, this velocity gradient tensor, so this is a velocity gradient tensor, this plays a fundamental role because using this velocity gradient tensor I can actually define the time rate of change of that deformation gradient. So, I can define this guy. What is capital F a function of? Is that a function of spatial coordinates or material coordinates? Is capital F a function of spatial coordinates or material coordinates? So, x, this is the spatial coordinate, it is a function of material coordinates. You are differentiating something that is a function of material coordinate with respect to material coordinates, the resulting terms will be functions of material coordinate and time. So, you are trying to differentiate Fij with respect to time. Okay. So, the way this is defined, you can define this is using this equation, and what we say is that dxi dot is given by Fij dot times dxj. Okay. And from here you can write that your Fij dot is going to be del xi dot over del capital Xj, and that is basically, that becomes, so this is, so del xi dot, this is the time derivative of a spatial coordinate. Okay. Time derivative of a spatial coordinate, what is that going to give us? Velocity. Okay. So, xi dot is basically again del y del t of phi keeping capital X constant, which is basically our velocity in the Lagrangian field terms and equal to u in the spatial field terms. Okay. So, you can either write it like this or this. So, we are going to choose to write it like this, and what I am going to say here that it is del u. So, xi dot, let me write like this. So, xi dot is going to be ui dot. So, this is basically del ui over del x small j, and then del x small j over del x capital J. I could have written instead of j, I could have written k also to avoid any confusion. Okay. The only reason is k is a dummy index. Okay. K is being summed over, and I do not want to coincide with I or j, otherwise that will ruin the meaning of this expression. Okay. If I had written small I or capital J here, then whichever one I write, that would be summed over, then your free indices won't be the same on both the sides. So, the again usual practice is to choose a separate index, and if the algebra is helping you out, it will help you out and help you replace the indices with the existing ones. Okay. So, this is what you get for time derivative of the deformation gradient. So, you can write it in the direct notation as this. So, this is gradient of velocity del ui by del xk. Okay. This is gradient of velocity times the deformation gradient. Okay. Just to make sure that we are talking about a summation, you can put a dot here. Okay. Because in this course we are, when we don't put any product sign in between, then it usually means tensor product. There's no tensor product happening here. Okay. So basically the rate of deformation, that is captured by this f has a very important term in it, which is the velocity gradient term. So the only reason for me to do this derivation, besides helping us derive the Reynolds transport theorem, is to emphasize that velocity gradient is indeed a very central term or a central kinematic expression in fluid mechanics. Okay, and there are a lot of places where this velocity gradient tensor will appear again and again in different ways. So let us look at this velocity gradient tensor a little bit. Okay, so just like I had said towards the end of our review of index notation, you can write down a second order tensor, you can decompose it into a symmetric and an anti-symmetric component. So I can write my velocity gradient tensor usually like this, where this T denotes transpose of the matrix that represents velocity gradient tensor. Okay, I'm never saying that velocity gradient tensor is a matrix, it's a tensor. Okay, the transpose is supposed to tell you that, okay, we are writing. So basically if you write this in index notation, then it will look something like, let me just first complete this. So in the index notation, this will actually look like, so del u I over del x j e hat j e hat I is half of del u I over del x j e hat j e hat I plus del u I over del x j e hat I e hat j, and then a plus half of same things with a minus sign. Okay, that's what transpose does. Okay, that's what transpose means. So again, in individually in these expressions, I and j are dummy indices. Okay, I and j are dummy indices. So here I can swap I with j and j with I. I can write I as j and j as I, and that will help me write the basis tensor e hat j e hat I as same in all. So I will get half of del u I by del x j plus del u j by del x I times e hat j e hat I plus half of del u I by del x j minus del u j by del x I e hat j e hat I, and on the left hand side we have del u I by del x j e hat j e hat I. So this tells you that the particular component of velocity gradient tensor, when you decompose it into symmetric and anti-symmetric components, is going to be, so del u I over del x j is going to be half of del u I by del x j, and then half of del u I by del x j minus, oh, marker no. Okay, so in rest of this course, it may happen that I end up writing just an expression like this. Okay, I may end up skipping writing these tensor bases all the time. Okay, things get cumbersome if you are keeping a track of these, and in the exams, if it's not a question of particularly index notation that you need to simplify, it is okay if you want to skip these as well. But if it's a question that is asking you to prove something using index notation, then it wouldn't be wise to skip them. Okay, so there's a degree of freedom that you can that you can enjoy while doing this algebra here. So the important point that I want to highlight in this decomposition is that usually this decomposition is symbolically represented as S plus omega, where this S is called the deformation rate tensor, or sometimes simply deformation rate or rate of deformation, and this is called the rotation rate tensor. Now, how come they are classified like this? Okay, what is the physical interpretation of classifying these two? Didn't we just say that okay, this is the rate of deformation gradient, so grad u should technically be the deformation rate tensor. What is this rotation rate tensor doing separately in this? Okay, so this requires a little bit of work that we will do just now. So we will show that why one of them is capturing all of the deformation that is possible for a fluid particle, and the other one is actually capturing the rigid body rotation of a fluid particle. So what you can think of is, let us say you have a fluid particle that is oriented like this initially. As it deforms, then the action of S would be to basically introduce a, let's say, a rate of deformation in it. Maybe it will make it like this, okay, and then the action of omega is usually to do a rigid body rotation of this guy. Okay, it's a rigid body rotation. We'll show how it is a rigid body rotation. So this goes back to very old fundamentals of mechanics by Cauchy, in which they said that any deformation or rate of deformation, you can break it down into a deformation. Obviously there is translation that is happening, translation plus deformation plus a rigid body rotation. You can decompose any deformation like that. Okay. So let's look at how we get to this meaning. One is a deformation rate tensor, other is a rotation rate tensor. Let us try to get this physical meaning out of the velocity gradient tensor. So before we try to do that, let's just jog up our memory and practice of index notation. So let us say you have an Aij times Bij term, and let us say A is symmetric and B is antisymmetric. Then what is the value of this Aij times Bij? Huh? 0. How do we prove it? How do we prove it's 0? So both I and j are which kind of indices? Both I and j are dummy indices. So I can write this expression to be Aji Bji. Now by definition of symmetric and antisymmetric, I know Aji is actually equal to Aij, but Bji is equal to minus of Bij. So Aij Bij is minus of Aij Bij. So quantity is minus of itself, it's 0. Okay, that means it's equal to 0. So whenever you're, yeah, no, of course not. S and F dot are totally not same. F dot is the rate of deformation gradient. This is the physical meaning that we have ascribed. That is the mathematical definition. We define the deformation gradient. I am defining the rate of that deformation gradient. Okay. This is what we are trying to say is, in the deformation gradient, there are actually two things that are hidden. Okay. One is actual deformation, the other is rotation. Okay. This S is trying to bring that out. So if you, I don't know if you guys have had continuum mechanics course, but if you look there, then usual practice is to decompose this F in using a UV decomposition, in which one is a rotation matrix, the other is a stretch matrix. Okay. So that stretch matrix doesn't necessarily mean longitudinal stretch. It also has shearing in it. Okay. So in a way you can think of this S as encapsulating the time derivative of that stretch matrix, and this as encapsulating the time derivative of the rotation matrix. Okay. So when you multiply a symmetric and an anti-symmetric tensor, the product is 0. This multiplication is not straightforward. Okay, which kind of multiplication is this? So this is aij times bij. What does this mean? Does it mean this? Does it mean this? So if I write it like this, then this will be actually equal to aij bjk. Okay, that is what this dot product will be. Okay, usually this is also called an inner product, but you don't have to remember that. This type of a product is called a double dot product, and it is usually denoted by this, and this is actually equal to aij times bij. So to look at this physical meaning, that one is telling us the rate of deformation rate of deformation rate tensor. Then what I am going to do is, let us consider 2 points, 2 spatial locations in a fluid. Okay, now we are, as we move down in our discussion, you will see me changing the words from deformable body to fluid. Okay, so we are looking at 2 spatial points, and there is fluid everywhere, and there is some flow that is happening, and let us say the distance between these two. So the position vector between the two is dx, and the distance between them is basically ds, which is ds square is dx dot dx, or dxi dxi. Okay. Now let us differentiate this in time. Let us differentiate the equation in time. What do we get? We get 2 ds times ds dot is actually equal to 2 dxi dxi. So this is basically giving us del vi over del xj dxj and then dxi. How did I write like this? So the way to write dxi dot like this is, so for this you need to consider, let us say this is x1, this is x1 plus dx. Okay, and then what do? We will write the, how do we write? How do we write dx dot like this? Huh? How do we write it like this? So you can expand in Taylor series and then get this. Okay, if you don't understand that, don't worry. When we look at the rotation rate, then things will become more clear. So the 2 cancels out, and what we get is, I can divide by ds square on both the sides, and what I get is 1 by ds times ds dot is equal to del vi over del xj dxj dxi. So dxj by ds, dxi by ds separately. Okay. So dxi by ds is basically the unit vector, ith component of the unit vector. Dxj by ds is the jth component of this unit vector. Okay. And what about this tensor? The tensor dxj over ds and dxi over ds, is it symmetric? It is symmetric, right? It is equal to dxi over ds dxj over ds. The product is symmetric. If you swap I and j, there is no minus sign that appears. So this is symmetric. So now we have a del vi by del xj times a symmetric tensor. By what we did there and here, this means that this expression is actually equal to, going to be equal to, let's say, let's write it like Sij plus omega ij dxj by ds times dxi by ds. And we know that product of a symmetric and an anti-symmetric tensor is going to be 0. So, this is actually equal to Sij dxj by ds dxi by ds. Yeah. Oh. Yeah. Very well designed LHC. So, this del Vi by del Xj is Sij plus omega ij. Okay, and the product of these two is going to be 0. So, this is equal to Sij dxi by ds dxj by ds. So, what this tells you is that the rate of change of length between two particles. Now, again, what does it mean by length between two particles? What we are actually getting is, let us say there was a fluid particle at this spatial location, a fluid particle at this spatial location. What is the rate of separation of these two fluid particles? Okay, x1 and x1 plus dx are anyways spatial locations, they are not separating apart. The fluid particles which are on x1 and x1 plus dx are separating apart. Okay, so be careful when you are, yeah. What RHS? This one, it will become clear to you. Just give me 5 more minutes. Okay. So, there is a fluid particle here, there is a fluid particle here. What is the rate of separation of those per unit separation? So, if you think about it, it is like the rate of engineering strain that you guys know. Okay, engineering strain is the rate of the change of length per unit length. Okay, per unit original length. That is what this is. Rate of change of separation between the two particles per unit original separation, and that is directly given by Sij. Okay, that is directly given by Sij here. I should write del ui instead of del vi. Okay, so this should show to you that per unit separation, the rate of change of separation is actually directly given by this Sij tensor. So, this shows that Sij captures the local stretch or the rate of this stretch. Now, to get the meaning of this omega, what I am going to do is, again I am going to consider these two particles, and this time instead of looking at just the rate of separation between the two, I am going to look at their relative velocity. Okay. So, relative velocity is a more general term, more general quantity that you could look at instead of rate of separation. The rate of separation is going to be relative velocity dot with the position vector between the two. Okay, dot with that unit vector, that is what rate of separation is going to be. I am looking at a more general quantity now, and this now we will easily get what is this, how did I write this dx dot. So, what I do is I write, so I say that u at x1 plus dx minus u at x1 is actually du, and I can write it using the Taylor expansion. So, u at x1 plus dx I can Taylor expand, and what will I get? U at x1 plus del u by del x at x1 times dx and so on. Okay. So, du is basically going to be velocity gradient dot with dx. Okay, to be exact, actually it's going to be dx dot velocity gradient, and what you will get is exactly this guy. You will get del ui over del xj dxj. So this is the relative velocity between the fluid particles which are at x and x plus dx. Okay, you can read this as x1 or x plus x. It is okay. Yeah.
Omega ij was assumed to be 0.
No, omega ij is the rotation rate tensor which is by definition anti-symmetric, and so when I cancel this within a product means the product is 0. Omega ij is not 0. The product of omega ij and dxi ds dxj ds is 0, not omega ij is 0. So when I write it like this, it should mean that the product eventually with this term is going to be 0, so I am going to ignore it. Yeah, this guy is symmetric. So if I am multiplying it with the anti-symmetric part of the velocity gradient tensor, that's going to be 0. Okay, so the relative velocity is like this. So basically here what we had was the relative velocity. Okay, so this term when we differentiated it in time, you can think of it like relative velocity dot with the dx vector. Okay, that is what our rate of separation was. Okay, so that is why you have a relative velocity dot with the dx vector here, which gave us rate of separation. Now we are writing general relative velocity, and this is what we get. Now let us break it into two components. Del ui by del xj we know is going to be, so du, let's write this using index notation as dui is del ui, is this part visible on the board? Del ui by del xj times dxj, which is equal to, so dui I can write as sij dxj plus omega ij dxj. Okay, and now we are going to recall that omega ij is anti-symmetric. So what, how many independent components can an anti-symmetric matrix have? 3. So we had said that there is a something called a dual vector that is associated with every anti-symmetric tensor, and the relation between this omega ij and that dual vector is that omega ij or any anti-symmetric tensor is given by minus half epsilon ijk omega k. Okay, now this is just a choice, both minus and half are just choice for us. As you will see when I keep doing the algebra here, it will simplify into a very known type of an expression to you guys. So this is just a choice, these are just constants which you should not think they have been derived. Okay, basically what I am saying is omega 1 2 is going to be what, minus half of some omega 3, omega 2 3 is going to be what, half of some omega 1, and omega 1 3 is going to be, omega 1 3 is going to be what, 132. What is epsilon 132? Half of omega 2. So basically what I am saying is, let us write this anti-symmetric tensor in a matrix form. If you think about it, let us write it like this. So some minus half of omega 3, half of omega 2, half of omega 1, and then the negative of these. Okay, whatever values of these omega 1, omega 2, omega 3 are, we don't care. Okay, in general you would have written it like 0 0 0 then a b c. I'm just saying okay, this is what a b c are. Okay, actually this is minus of half of omega 1. because this is epsilon 2 3 1, which is 1. So you have a minus half. Okay. So this omega is called the dual vector, and now there is a way in which you can invert this relation also. Okay, and the way to invert this relation would be, so what are the free indices on both the sides? What are the free indices in this expression? I and j. Okay, so what I am going to write, multiply this whole expression is with epsilon Lij. Okay, I am going to multiply both sides with epsilon Lij. So I am going to get epsilon Lij omega ij equals minus half epsilon Lij epsilon Kij omega k. So I have written epsilon ijk as Kij. I can do that. Okay, as long as I maintain the cyclic order, I can do that. So now we have something, actually no, I should not have written it like this. It is okay. Actually, I should have written epsilon Lij as minus half epsilon Ijl epsilon Ijk omega k. And now we have something familiar. So the first index of these two epsilons that are multiplying is the same. So we can apply the epsilon delta identity, and we'll get minus half of, what will we get? Epsilon ijl times epsilon ijk. What do we get? Delta jj delta lk minus delta jk delta lj times omega k. What is delta jj? 3. What is delta jk? Times delta lj, again delta lk, right? This is what? What is this? Minus, so this is minus omega l. Okay, you get 2 delta lk, 2 cancels out, you have a minus delta lk omega k. So I replace k with l, you have minus omega l. So epsilon Lij is equal to minus omega l. Okay, so we have just inverted this relation. Now let us substitute this omega ij in terms of the dual vector here. Okay, let us substitute that here, and then hopefully things will become more clear to you guys. What is this omega ij doing? So we get dui equals Sij dxj plus minus half epsilon ijk omega k dxj, which I can write as, so this minus I can convert to plus if I change the cyclic order of epsilon ijk. So I can write this as half of epsilon I kj omega k dxj. And this is equal to Sij dxj plus, what can you see this term as? Epsilon I k j omega k dxj. What is that? That is half of some vector omega cross dx vector. Do you recognize this from somewhere? Relative velocity between 2 points is the rate of rotation cross with the separation. Going back to our first year APL 100, this is what we have. Okay, so technically this is the basic difference between rigid body dynamics and deformable body dynamics, is that this was not there for you guys so far. There was no deformation, So far you were doing rigid body dynamics, and in that you had this, which is why we call this omega ij to encapsulate the rigid body rotation of two fluid particles with respect to each other. What does that mean is, so similar to here, we had a point x and we had a point x plus dx. Let's say there is a fluid particle at these 2 points initially. So what omega ij is going to tell me is that how is this fluid particle going to rotate about the fluid particle at x or x1. Okay, technically this half omega is the rotation or angular rotation or angular velocity you can call, and this half omega is related to omega ij through this dual vector relation. Now every time calling and carrying forward this dual vector relation is not very efficient. So what I'm going to do now is using this inversion that we did. So we got that omega L is basically minus of epsilon L I j times omega I j. Okay, using this I'm going to write omega L, or I'm going to attempt to write omega L in terms of velocity gradient or something related to velocity gradient. Okay,
So omega is angular velocity or half of omega?
half of omega is the angular velocity, no? That is what you have. So omega, I mean, the don't get confused with the symbol. Okay, symbol is something that I'm using from fluid mechanics. Don't get confused with the symbol. You have half of omega as the angular velocity, and we'll just see in a minute how is this omega related to velocity. I'm going to remove this part. So you have epsilon Lij omega Ij. What can you say about epsilon Lij in I and j? Is it symmetric or anti-symmetric? Anti-symmetric. So if I write this as minus epsilon Lij omega Ij minus epsilon Lij Sij, it doesn't matter because this part is anyways going to be 0. Okay, epsilon Lij Sij is going to be a 0 vector. Okay, so I can write omega L to be minus epsilon Lij omega Ij plus Sij, which was what? Which was what? Minus epsilon Lij. What was this? Omega Ij plus Sij. So in I and j in the index notation, what was it? Del ui by del xj. Okay, del ui by del xj. Now again we have a minus epsilon Lij appearing here. If I shift the order of I and j in epsilon, then I can absorb this minus sign, and this is going to be equal to epsilon Lji del ui over del x j.
Del uj by del x.
No, no, I've swapped I and j, but in epsilon, not in this. Only then I can absorb the minus sign. No, epsilon Lji is minus of epsilon Lij.
But swap and swap it in the whole expression.
No, 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 why? I haven't swapped anything. I'm writing epsilon Lij as minus of epsilon Lji. There's a difference. If I had swapped, then this would mean it is equal to minus epsilon Lji del uj by del xi. I haven't written the minus here. Okay, I am absorbing this minus sign using definition of epsilon. I am not swapping I and j in the whole expression here. Okay, so this is actually useless because I still end up with a minus sign. You will see why absorbing this minus sign was important. So we get epsilon Lji del ui by del xj. What is this? Do we recognize this? Huh? Do we recognize this? First of all, is this a vector or what? This is a vector. This is the lth component of a vector. What is that vector of which its lth component? So if I write C as A cross B, what is the lth component of C? Curl. Yeah. So exactly. So lth component of C is basically epsilon L I J A I B J. If something like that appearing here, so this is actually this omega L is nothing but the lth component of curl of velocity. Okay. This omega L is the lth component of the curl of velocity, and this is how you are going to write omega L, epsilon L J I del ui by del xj, and this has a very specific name in fluid mechanics, and it is called vorticity or vorticity vector. And so half of vorticity is the local angular velocity in a fluid motion. Okay, half of vorticity is the local angular velocity in a fluid motion, and yeah, this is the whole proof. So just from velocity gradient, a simple innocent looking tensor, this is all the information that we can derive from that. Any questions so far? So all of this is given in the in chapter 2 notes that I have uploaded on the website. Please read this, ask any doubts, and by the way, these notes are not like textbook. Okay, so they are to help you understand textbook more. There may be some steps that are skipped in textbooks or some hidden text between the lines things that you cannot read. Okay, these notes are supposed to fill that. You cannot substitute them with, you cannot substitute a textbook with these. This is like a helping material for you guys. Okay, so every time if you read if you read these chapters that I'm uploading, you don't understand something, first refer to the textbooks. So I've given the additional readings next to the chapters, so take a look at those first. If you don't understand anything in that, then you can come and talk to me. Okay.